morning, or good afternoon if it's the afternoon when you're watching this, or hello if it's any other time of day. Hello. My name's Natalie Hogg, I'm a postdoc at the IFT in Madrid, and today I'm going to be telling you all about constraints on the distance-duality relation with standard sirens. So if you're ready, let's go. Come on, let's go! While we head to campus, let's recap what we know about standard sirens. A standard siren is a gravitational wave event with an observed electromagnetic counterpart, typically produced by the merger of two neutron stars. This makes them really useful for cosmology, as the gravitational wave signal allows the luminosity distance to be measured, while the counterpart enables an estimate of the redshift of the event to be made. The first and so far only standard siren event was observed by LIGO and Virgo in 2017. With this single event, a measurement of the Hubble parameter at redshift 0, or h0, was made, and the almost simultaneous arrival of the gravitational and electromagnetic signals meant that a large number of modified gravity models, which predicted a tensor speed different to that of the speed of light, were ruled out. The volume and precision of cosmological surveys is increasing all the time, and measurements of cosmological parameters such as h0, the matter density omega n, and the dark energy equation of state W are thus continually improving. So understanding what constraints we can obtain on various deviations from the standard paradigm of general relativity and lambda CDM is therefore increasingly important. In this work, we're interested in constraining a violation of the fundamental relationship between luminosity and angular diameter distances, which is known as the distance-duality relation. We can already use type 1a supernovae, which probe the luminosity distance, and baryon acoustic oscillations, which probe angular diameter distances, to do this, but could standard sirens improve the constraints? With only a single standard siren event, there will of course be no improvement on current results. So in this work, we created mock datasets to forecast upcoming constraints on a distance-duality violating theory that could be obtained by the Einstein telescope. The Einstein telescope is a proposed third-generation gravitational wave detector, which will be based in Europe. It will have 3 arms and be constructed partially underground, allowing for better sky localization and a reduction in noise compared to the current array of gravitational wave detectors. Now we've arrived in the office, here's the distance-duality relation. The luminosity distance, dl, is related to the angular diameter distance, dA, by a factor of 1 plus z squared, assuming that the spatial curvature omega k is 0. This relationship holds under 3 conditions. The first, that spacetime is described by a pseudo-Riemannian metric. The second, that photons travel on null geodesics, in other words they're massless. And the third, that photon number is conserved. We're going to find out how well standard sirens observed by the Einstein telescope will be able to constrain a violation of the third condition. We consider a mechanism through which photons decay into axions, a hypothetical light scalar field, through an interaction with intergalactic magnetic fields. The effect of this mechanism is given by this equation, where the parameter A can be thought of as the amplitude of this photon axion decay. It's this parameter we'll focus on today. The other terms appearing in this equation are h0, the speed of light c, the co-moving distance dc, and psi0, which is related to the probability of a photon converting into an axion as it travels over a given length scale, and it's of order 1. This mechanism changes the observed luminosity distance to an object from the bare or true distance, thus violating the distance-duality relation. So how well can we constrain this mechanism? To answer this question, we create 3 mock datasets using lambda CDM as a fiducial cosmology. We create a supernova catalogue following the specifications of the legacy survey of space and time at the Vera Rubin Observatory, which will observe around 9,000 supernovae up to redshift 1. That's a bit of a mouthful, so I'll refer to this mock dataset as LSST from now on. For the baryon acoustic oscillation mocks, we follow the specifications of the Dark Energy Spectroscopic Instrument, or DESI, which had its first light late last year. We create a DESI-like mock catalogue of angular diameter distance and Hubble parameter measurements up to redshift 3.5. As I previously mentioned, supernovae and BAO can constrain deviations from the distance-duality relation without standard sirens. However, when analysing the photon decay mechanism using supernovae alone, strong degeneracies appear between the amplitude parameter A and the matter density omega n. We can add the BAO data to break this degeneracy, but BAO come with their own issues. Specifically, a fiducial cosmology must be assumed to convert the angular scale on the sky into a distance, which could introduce some model bias into the data. Secondly, non-linear effects can change the location of the BAO peak in the galaxy power spectrum, and these effects aren't easy to model when considering theories beyond lambda CDM. Consequently, we introduce standard Sirens as a third dataset to provide more constraining power on the distance-duality relation violation caused by our photon decay mechanism. We create a catalogue of 1,000 binary neutron star events up to redshift 5, according to the proposed sensitivity of the Einstein telescope, with the assumption that all of these events will have an observed optical counterpart. If you want more information on how we created our mock datasets, then you can have a look at the appendix of our paper, or you're welcome to ask me later. Now, with our mock datasets ready, all that's left to do is run our MCMC analysis. Here we have the first results of our analysis. This contour plot shows the 1 and 2 sigma constraints on the matter density parameter omega n, the photon decay amplitude A, and h0. The grey dashed lines show the fiducial cosmology, and note that when A equals 1 we have no photon decay and hence no distance duality relation violation. The red contours show the parameter constraints from the combination of supernovae and standard Siren mock data, in yellow supernovae plus BAO, and in purple the full combination of mock data. We can see that the inclusion of standard Sirens improves the constraints on the photon decay amplitude by roughly a factor of 1.4, a relatively good improvement. However, these constraints are all obtained in the context of lambda CDM. What happens if there's also some modified gravity effect that we haven't taken into account? Will this change our constraints? In modified gravity theories with the time-varying Newton's constant, for example quartic Galileons, the propagation of gravitational waves is changed due to the presence of a modified friction term in the gravitational wave propagation equation. In other words, this delta tau function is non-zero. This results in the gravitational wave luminosity distance differing from the bare one, analogous to how the photon decay mechanism changes the electromagnetic luminosity distance. We now recreate our mock datasets with this modified gravity effect built in. Note that in theories with the time-varying Newton's constant, the supernova absolute magnitude is also changed, so the modified gravity effects will appear in both the gravitational wave and supernova mock datasets. We then run our analysis as before, acting under the assumption that the photon decay mechanism is the only way a deviation from the distance duality relation can occur. Here are the results obtained by rerunning our analysis using the modified gravity mocks. We can see that a large bias appears, resulting in a false detection of distance duality relation violation, in other words a measurement of A which is different from 1, at the level of 4 sigma. This bias increases to a huge 10 sigma if we use a stronger, though possibly less realistic amount of modified gravity in our mocks. This is solely due to the hidden effect of this modified gravity. So how can we get rid of this bias? Luckily, it's simple since we're using mock data and therefore know the cause of this effect. We parameterize the time variation of Newton's constant in the following way. And repeat our MCMC analysis, this time including the parameter GA as a free parameter. We end up with this result. Strong degeneracies are appearing in the combinations of LSST plus Einstein telescope and LSST plus DESI. In the case of LSST plus DESI, this is because the distance modulus for the supernovae contains contributions from both the photon decay amplitude and the modified gravity parameter, Ga, and these two parameters compensate each other. The BAO are not sensitive to either, hence why the degeneracy appears in the yellow contours. In the case of LSST plus Einstein telescope, we would expect this degeneracy to be broken. However, changes in Ga can be partially compensated by changes in omega n. Since omega n is not well constrained by standard Siren data, the degeneracy between A and Ga remains. However, the full combination of data is able to correctly recover the fiducial cosmology once more, and we achieve roughly 3% constraints on the photon decay amplitude A, even when the modified gravity parameter Ga is allowed to vary in our MCMC analysis. There's one other factor which we haven't yet considered, and that's screening. In modified gravities, with an additional scalar degree of freedom, the scalar field can develop an environment-dependent mass, and in regions of high density or at small scales, the scalar field can become heavy enough to screen out the modified gravity effects. Both supernovae and compact object mergers are sufficiently extreme events that screening mechanisms could be present. But what happens if only one of these two is screened? This plot shows the constraints obtained on our cosmological parameters and photon decay amplitude when the modified gravity effects are screened around the supernovae. This means that the modified gravity effects are only present in the standard Sirens dataset. Consequently, the LSST plus DESI combination is able to recover the fiducial cosmology, but the two combinations which contain gravitational wave data are not, due to the biasing effect of the modified gravity. Once again, we detect a false violation of the distance-duality relation due to this effect. If such a situation were to arise in real data, this could be a smoking gun for the effects of a modified gravity model with this type of screening behaviour. In summary, standard Sirens observed by the Einstein telescope are going to become an excellent complementary probe of fundamental cosmology in the coming decades, but care must be taken when using them to analyse non-standard theories, as changes to either the electromagnetic or gravitational wave luminosity distance could bias the measurement of the other, as we have shown here. Thank you so much for watching. I hope you enjoyed my talk, and I'm really looking forward to discussing this talk and everybody else's at the discussion sessions or on Slack, via email or via Twitter later on. So thanks again for watching, and see you soon.